After covering the basic rules by which sensory research gets completed, we're going to take a look at vision. Vision is probably the easiest sense to deal with because it's easier to show visual stimuli than it is to work with some of the other senses. Vision is also one of the senses that is focused on in research more than anything else, mainly because human scientists have a bias towards studying vision, as vision is very important for human communication. Now, based on the rules that we were talking about, if vision is what we're going to study, one of the first things we have to do is understand the receptor for it. And in fact, to understand the receptor, we have to understand the energy source itself. What is light? And so this, of course, goes way outside the purview of psychology and, in fact, leads us right into physics. So we could take a general understanding of the physical properties of light from the field of physics itself. Light is essentially an electromagnetic particle that's always the same. And the fact that it's always the same is going to be an important part of this story. We can, if we want, to simplify the whole story, given that this is not a physics class, and just essentially refer to the electromagnetic particle, which is the photon of light, to just essentially be a tiny little ball, like a tiny baseball. And in fact, we're going to play with the idea similar that way. So if a baseball were dragged across the surface of water, it would produce a lot of waves. And so you'll have this particle and this wave component of light that you typically hear about. Light is both a particle and a wave. Now, it's not the particle so much that actually has relevance for us in determining the experience that a person has, but much more the wavelength that it generates. If you take a look at the electromagnetic radiation that's known to exist in the universe, it extends from gamma rays, which are the strongest waves and therefore have the smallest wavelengths, all the way down to radio waves, which are very long and are, of course, the weakest waves. Now, notice on the scale, this is not a linear scale. This is a logarithmic scale. Gamma rays being the strongest, then we go down to X-rays, ultraviolet, then we get into the visible spectrum, and then infrared and radio waves. This is not drawn to scale either. The amount of visible light that we see in the center is really not special in any way other than it is our eyes that have adapted to detect the electromagnetic radiation in that tiny range. So it's not that the light is unique in some way, it's just another wavelength of electromagnetic radiation, and we have eyes that have adapted to detecting that particular range of wavelengths. Now, let's play a game with this concept of light. Let's suppose that an electromagnetic particle is just like a baseball, and we shrink ourselves down tiny, tiny, tiny so we can catch a photon of light. In this thought experiment, what we're going to do is we're going to catch gamma radiation, a single particle of electromagnetic radiation in the gamma ray range. We catch it, and now we're going to throw it much more slowly so that it has less energy. Now we're going to throw it with much less energy. And in fact, we're going to throw it with so much less energy, it's going to be a radio wave. Now, because this is a thought experiment, we can now get in front of our own throw and then catch that radio wave that we just generated. Having stopped that particle, we can now throw it with more energy so that it is now infrared light. Now we can jump ahead of our own throw and catch that particle and throw it with even more energy so that it becomes an X-ray. And then we can get in front of that particle, which is an X-ray, and now throw it with less energy so that it becomes blue light. And we can go through the visible spectrum this way by catching the particle and throwing it with progressively less energy so that it turns from blue to green to yellow to orange to red. And we can hit all of the various colors along the way. Each time we're catching and throwing the same particle. Now my question to you is, what's actually changing? If we're catching a particle and we're throwing it with a particular degree of energy so that it would be red light, and then we catch that same particle and throw it with more energy so that it becomes blue light, then we catch that blue light and then we throw it with less energy so it becomes green light, what's actually changing? Well, the amount of energy is changing, and that energy is reflected in the wavelength of the light itself. Did the particle ever change? No. The particle is always the same. It just changes the amount of energy that it has each time we throw it. Therefore, if we take the same particle and we can throw it so it is either blue light or green light or red light, what color is the particle? Well, the answer is it doesn't have a color. The particle of electromagnetic radiation that we're throwing is the smallest unit in the entire physical experience that generates light or that would produce light. So the particle itself is actually considered colorless. It has no color. If the particle had color, then it would have to emit smaller particles that would go into our eye so that we could see it. Instead, the particle itself is the smallest unit, and the concept of color doesn't make any sense. And if this is the case throughout the entire universe, that the particles that allow us to experience light of different colors is always the same thing, then what physicists tell us is that the entire universe has no color. It is colorless. There is no red, there is no green, there is no blue, there's no colors that you ever experience. Everything is uniformly not colored. But of course that sounds rather bizarre because you see color all the time. You get dressed in the morning by matching the colors of your clothes together. What's actually happening? The wavelength of that particle, the wavelength associated with that particle, goes into your eye, generates an action potential, and based upon the amount of energy it had when it reached your retina and affected a cell, generated a series of action potentials that were sent back to your occipital lobe that then generated an internal experience of a color. So where is the experience of the color then? It's actually inside your head, through a process which is not fully understandable as of yet, but perception of color exists in your head, literally inside your brain only, but it is not outside of your own body. This strange set of circumstances really kind of changes the way you may see all of experience, because the same type of argument can be applied with touch and smell and taste and all your other senses, that you have a source of control outside your body, like a chemical or a force that impinges upon a receptor, and then it's the receptors generating the action potential that gets sent into your brain, and then some circuit simply gives you an experience of an event which allows you to distinguish between other types of energy sources. But when you talk about something being red or green or blue, Those are things that exist inside your own internal experience that are literally not outside of you. Consequently, you start to see of all of your six senses, remember balance being your sixth, that your experience of all things is really generated by the circuitry of your brain and is not an actual thing that's outside your body. So just as I've explained to you in terms of the Weber fraction, that your experience detecting the intensity of a stimulus is frequently not the same as the actual energy source outside your body, now you're even saying that the internal experience you generate is completely fabricated by your brain and has nothing to do with the source of energy outside your body. So let's take a look at this question. The experience of color is a B, perception. At this point, we need to make a clear distinction between sensation and perception. Sensation will always refer to the actual experience that is occurring from the actual physical stimulus that's outside your body. Perception is what you become consciously aware of. It is a combination of the sensation that comes in your nervous system plus all of the learning and memory that was part of the definition of perception that is incorporated as a result of that sensation coming in. So if what you perceive is actually dependent upon your prior learning and memory, what we're going to see is that your life history with certain events will come to dominate how you experience something today. You're always more strongly controlled by your past experience modifying what's currently happening, as opposed to you having an accurate understanding of what's happening at any one moment. That's going to be the basic underlying rule that you're going to see in this chapter. To get there, we have to work through some of the other strange aspects of vision. If you take a look at your eye, there are only 3 cones that detect color. Now, you've heard of cones and rods in your eye. They are the types of cells that are in your retina. You may remember that cones are there to help you see color and that rods help you see black and white, more likely shades of lightness. Now, to be more accurate, what cones actually do is they are detectors of the wavelength of electromagnetic radiation that comes in your eye. Okay? Specifically, the wavelength. And the rods are specifically the detectors of the amplitude of the light that comes in your eye. So a wave always has a wavelength and an amplitude, and you have 2 separate receptors, one for each component of that wavelength. Cones are detectors of wavelength, and rods are detectors of amplitude. So that's why people generally say cones help you see color, because your internal experience of color is derived by the wavelength itself. And when you say rods help you see black and white, it's rods that help you see the intensity of brightness, which is reflected in the amplitude of the light wave. Now take a look at this screen. You can see red, green, and blue because you do have red, green, and blue cones, right? Which of course are not colored red, green, and blue. They're simply referred to as red, green, and blue cones because when you shine light of certain wavelengths into a person's eye, these are the words that they say they see. They see red, or they see green, or they say blue, depending upon the light wavelength that you shine into their eyes. Now there's another color commonly seen, which is not red, green, or blue, but it's also on the screen. What color is that? Well, It's yellow. And this is kind of a story you may have actually caught on some YouTube channels. What's the deal with yellow? I've just went through a whole long story where I explained to you the universe has no color. Everything is uniformly not colored. The wavelength of electromagnetic radiation that goes into your eye of only a tiny limited range gives you an experience of the visual spectrum, the colors from blue all the way down to red. Of the wavelengths that come in the visual spectrum, you have red, green, and blue cones. If the universe is not colored and you only have detectors for red, green, and blue, how could you possibly ever have an experience of yellow? Well, yellow comes as a result of the interaction between red and green cones functioning together. So in fact, what you have is nice evidence that color experiences are generated inside your brain and are literally not outside you. That is, first of all, the field of physics, which is in charge of studying this stuff, has said nothing is colored in the universe. Secondly, when you look at biology, you find that there are only detectors for the red, green, and blue families. For you to then see yellow means that you had to have had a brain that made it up, because it doesn't exist anywhere. And not only that, you don't even have a receptor for it. So where did it come from? Your brain made it up. And it's almost as far as we can actually go in the general story of internal experiences with color, because the manner in which you have an internal experience of any color, whether it's yellow, red, green, or blue, is really still not fully understood. It certainly should be related to the circuitry that exists in your occipital lobe, but exactly how this internal experience is generated is not clear. But this is important to keep in mind. If this internal experience of color is only existing inside your own brain, and it's not coming from outside of you, then it could be potentially manipulated so that you can see colors that don't exist or experience colors that are different than the wavelengths that are actually coming in your eye. And that's exactly true. One of the ways to kind of deal with this issue is to take a look at what's called the opponent process colors. You see the opponent process colors in the bottom of the page. Red and green are a pair, yellow and blue are a pair, and black and white are a pair. What these are color pairs that you could not have guessed at existing until you actually discovered it. That if you shine enough of the wavelength of red into a person's eye so that you fatigue the cells, and this is a little bit of a new story for us, but along the lines of habituation that we've talked about in previous chapters, if you expose a receptor to the same stimulus again, the receptor will become fatigued and turn off. If what you're doing is fatiguing a red color cone, your brain will generate the opposite or opponent color, which is green. Now, these are not necessarily opposite colors on a color wheel. These are just combinations of colors, red and green, that your nervous system has already made up. So if you fatigue the red color cones, you will actually get a green after image. If you do the reverse, where you expose yourself to a lot of green, your ability to see green will stop and you'll wind up seeing red afterward. There's one place where you actually commonly have an experience of this, and that is when you see a blue dot after someone takes a flash picture of you. In a formal photographic setting, a strong light bulb that flashes at the moment the picture is snapped will have somewhat of a yellowish light. And because the color cones that help you experience yellow are fatigued from the brightness of that light, you will always see a circular blue dot floating in front of your face afterward. Now, hypothetically, if you had a different shape other than a punctate bulb, so that, for example, you looked at a bright yellow neon X from a large sign, would cause you to wind up seeing a large blue X afterward as an image. And the same would happen as well if you looked at a blue neon X, you would wind up seeing a yellow one afterward. If you stared at a green neon sign that said "Eat at Joe's," you would then see a red "Eat at Joe's" floating in front of your face. When you get down to black and white, what's really happening is this. Black is going to be a scenario in which there's no light. And we talked about that earlier in the chapter. When there's no light in the room at all, you become aware of light flashes, which are generally whitish. And if you expose yourself to too much white light, so a large amount of light all at one time, you'll become temporarily blind. That is, you'll experience black. So each of these color combinations work in conjunction with each other, and you could not have predicted that they actually would have existed by any biological means otherwise. This is actually something that really starts to show up in the 1800s as there's more control over light bulbs, light filters, and so forth, where you can change the intensity of various colors and start to experience the opponent process colors. Now, the strangeness of color experience doesn't stop there. You don't just have these opponent process colors, you now have a process in which the color that you experience, because color is purely perceptual and internal experience, is going to be dependent upon the relative proportions of light wavelengths that are reflected in your eye from the object you're looking at. So, for example, when we talk about seeing something that's blue, we just generally take as an assumption that the entire thing is one uniform blue. But in reality, for anything that you call red or blue or orange or yellow, there is very likely other wavelengths mixed in with it. And the mixture of the various wavelengths that exist in the natural environment will modify how red or how blue or how yellow something looks, because the other wavelengths will be mixed with it. And in fact, you could mix it with fainter light so that it seems dimmer, or if you have a very intense laser light, that would be extremely strong, and it would be one uniform color, as well as laser light is a stream of electromagnetic radiation that is very strictly held to well-defined limits, so it's all the same. This leads to research that starts to show that when you ask about what color is any particular object and why is it that color, there are a couple of things you have to pay attention to. One, the amount of light, and two, the relative proportions of wavelengths. These things make up most of the story of why you see one color as opposed to another. So, for example, if you're sitting in a blue chair right now, you could ask yourself, why is the chair blue? Well, the chair would be blue because the light in the room that bounces around would absorb almost all of the wavelengths other than blue. For you to see the chair as blue, blue light has to hit the chair and then bounce off and then go into your eye, which means the other wavelengths are not bouncing off the chair. They are actually being absorbed by the chair, probably as heat energy. Now, we're keeping this in a very simple sense because realistically, whatever fabric and the types of light in your room are probably going to emit a variety of different wavelengths, but some things will have a predominant wavelength that bounces off of it, and that wavelength will then be associated with a color that a human being describes it to be. So if you see a blue chair, it's because of the full range of wavelengths that are being emitted from natural light coming through the window or even the light bulbs that are operating in the room. All of those wavelengths are being absorbed by the fabric of the chair except for the blue, which is bouncing off and going in your eye. And because blue wavelength bounces off the chair and goes in your eye, you see that chair as blue. Now, what if, because blue is an internal experience that is unrelated to the physical wavelength of light that's outside of you, you took that chair and placed it in a room that only had red light in it? Would the chair still be blue or would it be red? Well, if the chair under the conditions of natural light, that is, of the entire visible spectrum, was seen and you referred to it as blue, you could take that chair, place it into a room, and show it to a person who was blindfolded and had never seen that chair before. And in that room, there would only be a bright red light. That chair would have to be red at that point because the only light in the room is a bright red. You're controlling it. This is an experiment that you're performing. You're only allowing bright red light into the room, and that's the only wavelength that exists. Now, much of that red may get absorbed by the chair, but not all of it will, and any light that bounces off will have to be red. So the chair must be red. So if you had taken a blue chair and put it in this room that only had red in it, brought in a person that has never seen it before, and then unblindfolded them and let them see the chair, they would say it was red. But if you, having seen the chair before under normal conditions and referred to it as blue, and you had to pick the chair up, carry it to the laboratory yourself, set it down, and then close the door, turn on the bright red light so that was the only light in the room, you would not see the chair as red. You would see it as blue. And you would see the chair as blue because you had already learned that it was blue. Because you saw it blue before, you picked it up and carried it to the room. It was blue the whole time that you walked over there. You put it down, closed the door, turned on the red light. You will still have an internal experience of that chair being blue. It won't become red to you. It'll become reddish because of the red light, but you will still have an internal experience primarily that the chair is blue. And what you're actually seeing in this case, what's very important about this aspect of color constancy, is that your direct experience with an object, that you learn and remember what your experience was, becomes the dominating factor in determining your current experience with it. So the chair must be red under a red-only light condition, but you will have an internal experience of it being blue because you learned that it was blue originally. Now that seems rather odd. In fact, it's nice to focus on vision, to go through this whole stream of events that seems so unrelated to what is natural to most people. First, the universe is colorless. Second, you only have 3 color cones, but you see colors that don't exist, like yellow, for which, one, they don't exist outside your body. Secondly, they don't exist because of receptors. Then, the experience of a color largely comes from your previous experience with the object rather than the experience you must be having at any one time. it really throws off your entire understanding of what a perception is. And these basic rules, even though these are specific for vision, general rules like these apply for all of your sense systems. As a result, your prior learning and memory with various stimulus events in the environment largely determine how you experience new events themselves. So in the old internet meme of whether or not a dress was either blue or gold was largely determined by your history of looking at dresses under similar light conditions. Many psychologists have looked at that issue, and you can make a person see the dress as either blue or gold depending upon the kinds of dresses you show to a person first, which establishes a set of memories which will then come to dominate the ultimate test of what color you think the dress is. So let's take a look at the questions related to this. The color that you experience of an object depends upon what? Well, the answer here is E, all of the above. The context, that is the social context, even the historical context of that object with you, the proportions of reflected light that are on it, your previous experience with it, even what you heard about it, which was not something I even mentioned, but if you had a trustworthy source tell you something was red or blue and you've never seen it before, you would have a tendency to see it as red or blue. It might not completely eliminate your direct experience, but it very well may modify what you experience if you had heard from a trusted source that some color was going to be seen when she looked at the object. Now this leads us to a broader story of questions regarding perception, because that's really where we're focused right now. And one place to kind of get started with this broader concept of perception is to take a look at the Necker cube that you see on the screen. The Necker cube is probably one of the first simulated three-dimensional objects you ever drew, and you probably learned to draw them sometime back around 5th grade. You just basically draw one box and then another box kind of askew from it a little bit, connect the lines, and then you'll have it. Now I've placed one wall of the Necker cube in blue so we can use it as a reference. Take a look at that Necker cube. Is the blue wall in the back of the cube or in the front of the cube? As I've learned from using this for many, many years, about 80% of everyone who looks at it will perceive the blue wall as being in the back, which means the cube to them appears to be coming out and to the bottom right. That's the way the cube appears. It comes out, in the simulated three-dimensional, but to the bottom right. For those of you that see the blue wall in the front of the box, the cube appears to be coming out and to the upper left. Okay, so take a look at that blue wall and try to imagine it in the front. The box is actually coming out toward you, but to the upper left. So you can make the blue wall appear to either be in the back or in the front. And this is, of course, a perceptual phenomenon because what you're sensing is just lines and a color blue and some white sides as well. But you can make yourself see the blue wall in the back or the front at will, switching it once you learn that it could be one place or the other. Now, one of the issues that you have about this cube is that you can see the blue wall in the front, or you can make yourself see the blue wall in the back. But now that you know that you can perceive it in the front or the back, see if you can do this. Try to make yourself see it in both the back and the front at the same time. That's actually something most people can't do. In fact, I'm not aware that anybody could do this. The blue wall will either be in the back or the front. You can switch it back and forth, but you can't make it be seen in the back and the front at the same time. Why is that? It's that way because you only have one attentional resource. You can only pay attention to one thing at a time. And in this particular case with the Necker cube, you have to perceive the entire object as having the blue wall in the back or the entire object of having the blue wall in the front. But you cannot make the entire complex image appear to be in the back and the front at the same time because you have to arrange your attentional resources to focus on just one or the other. This is actually related to a very important part about sensation and perception and something that you are probably have an intuitive feel for, despite the fact that many people like to brag about how well they can multitask. You have one attentional resource, which means you can only pay attention to one thing at a time. If you can only pay attention to one thing at a time, then when you multitask, you are dividing your attention across the various things that you're doing. Consequently, if you pay attention to one thing, it can get 100% of your attention. If you're paying attention to two things, then each one gets 50%. If you're paying attention to four things, then they each get a quarter. If you're paying attention to five things, they each get 20%. It goes on like this in a straightforward algebraic fashion. You simply divide the amount of attention you've got by the number of things you have, and that's how much each item of attention gets. As you increase the number of things that you're paying attention to, you are paying attention to things so little that errors will start to occur. Much of the research on this kind of work was referred to as workload, and it actually got started back in the 1960s in part as research to try to understand how well the astronauts that were planning a trip to the moon would be able to operate the internal switches inside of the capsule. In the 1960s, the capsule that the astronauts were flying to the moon was considered so complicated that the engineers were concerned that the astronauts would make a mistake. And of course, if they make a mistake, they might wind up dying. So as a result, NASA hired psychologists to evaluate workload, that is, how much you could pay attention to, get an idea of the likelihood of mistakes occurring with three astronauts in the capsule. Other aspects of attentional resource that you commonly hear about today are things like driving and cell phone use, which should be obvious. If you're driving at 40 miles an hour and you take your eyes off the road to read a text for 1.5 seconds or 2 seconds, you will have progressed far enough down the road that you might not be able to stop if somebody else stops very rapidly and unexpectedly, causing a rear-end accident. Before cell phones existed in the 1990s and you started to hear about distracted driving, there was the cocktail party effect. The cocktail party effect was the idea that if you're talking to somebody at a party, but you're trying to eavesdrop on somebody else's conversation, you have to split your attention between the two conversations. And as a result, you only wind up listening to half of the conversation of the person you're talking to and only get half of the conversation from the other two individuals conversing that you really want to listen to. Another concept in perception is a process called Gestalt perceptions. Gestalt perceptions are a process discovered during the very earliest time in the field of psychology. And in fact, whenever you see German words in the field of psychology, it is typically very old information, stuff from the very beginning of the time of psychology, because psychology got started in Germany, much of its roots were there, and so all of the early research was written in German, and we still have those words today. So the term Gestalt in this context referred to the experience of a stimulus as a whole, the entirety of the object. One of the things that psychologists were doing back in the 1800s in the early psychology laboratories were trying to understand consciousness. And consciousness was too broad of a topic to evaluate itself, so they took portions of consciousness and tried to study specific aspects of it, like memory or sensation or perception. And in fact, in this particular case, a lot of research was done on visual illusions because the researchers were concerned with the process by which a person would consistently misperceive an object even when they knew that the object was something different than what they felt they were looking at. And a nice example of that is this image on the screen here. If you take a look at this image, you probably have a perception that none of the vertical lines are parallel with each other. In fact, they all seem slightly crooked, right? A little bit wider at the top and smaller at the bottom, and some of them are a little wider in the bottom and thinner at top. But actually, if you take a ruler or some measuring device to them, you'll actually see that all of the lines in this image are completely parallel. The reason why they don't appear to be parallel, as you could probably guess, has something to do with the black and white boxes and the specific way in which they're arranged. And that's exactly correct. The black and white boxes have an influence on your visual system to make those vertical lines appear as though they're crooked, despite the fact that they're not. You could take a moment, stop the video, make this full screen, and take a piece of paper, make a little measuring device, and you'll see that every one of those vertical lines is completely parallel to all the others. But this type of visual illusion started a history leading clear up to today, where psychologists study visual illusions specifically because it gives you insight into understanding how the human visual system operates and why specific types of illusions occur and other ones don't. Now, vision is an easy stimulus to work with, as I've mentioned before, but there are, of course, other types of illusions as well, like, and this is an old one we used to do in high school back in the 1970s. If you cut a square block of apple and a square block of potato, neither one having the apple skin or the potato skin on it, and then blindfold a person and have them pinch their nose shut so they can't smell it, they will not be able to tell the difference between the chunk of apple and the chunk of potato. And the reason is apple and potato are very easily distinguishable, which should be obvious. Apples are sweet and potatoes are starchy, but they have very similar textures to each other, which you might not really notice given that one is kind of like for an entree and the other one's maybe for a dessert. The thing about these experiences is that the sight and smell of the potato and the apple really establish the clear distinction between what is actually an experience of taste inside your mouth. You can go ahead and try that one on a family member if you want, apple and potato. Just be sure to cut the apple and potato carefully so they're about the same size, and you'll find some confusion in that case. People will have difficulty distinguishing between them. And there are a variety of types of events like this. Those, of course, as I mentioned, are a little bit more difficult to deal with, and you can't present them easily on an online presentation like this, but they are there. Now, visual capture. Visual capture is another perceptual aspect to understand, which is related to your natural experience of speaking to another person. When you speak to another person, you see that person, You see their lips and their jaws moving. You see the hand gestures that they make and their body motion. And it's all part of how they're speaking to you. It conveys meaning, the hand gestures and everything else. Because the person's speaking, it's also where the sound of their voice comes from. So under normal circumstances, the person speaking is the place where the sound is coming from. Once videos or movies, talking movies in the 1930s, were created, it led to a new form of perceptual illusion, and that is visual capture. The idea that when you see a person speaking and also hear a person speaking, you tend to think that the location of the sound comes from the place where you're looking. Which, of course, under normal circumstances, if you're speaking to somebody, you see them speaking and you hear them speaking, so that all makes sense. But now when you have a visual track and an auditory track from an old movie, or now you could separate them in your video equipment, the video and the audio do not have to be in the same place. And in fact, in movie theaters today, they make a big deal about how you're in surround sound. You go to a movie theater, you sit in your chair, and you see the visual presentation on the screen. But the sound of the people's voices is actually coming from around the room. You see in front of you an explosion occur on the screen, but you hear it from behind you. But you also hear it from the sides, just to make it sound like you're sort of in the middle of it. If you pay too much attention to the fact that the sound and the visual aspects are disconnected from each other, then you will start to disconnect your experience with the movie. So a nice example of that, even just to play it here, may be unnecessary to do, given that I'm speaking to you on a video, is to take a look at this.
Khan, as we know him today.
Here we have an old episode of Star Trek.
Name? Khan Noonien Singh.
From 1992 through 1996, absolute ruler of more than a quarter of your world. From Asia.
See, as Mr. Spock speaks, it's probably your natural experience to think that the sound of Spock's voice or Scotty's voice or Kirk's voice is actually coming from that one location of your screen. Now, of course, logically, you know their sound is coming out of the speakers of your computer or your phone, but your natural experience, without thinking about it, is that the sound is coming from the location of the visual aspect itself. And that is what visual capture is.
Mr. Spock, you misunderstand us. We can be against him.
So let's take a look at a few questions that are related to these things, that are connected to the aspects of perception that I've been talking about. First question: which principles are reflected in the following scenario? The new food you're served smells great but looks horrible, so you decide not to eat it. If it smells good but looks horrible and you decide not to eat it, it must be an issue of visual capture. D. The reason here is the visual aspect of the food itself is displeasing. You commonly see this with children. They may smell something that smells good in the kitchen, but when they see it, like salmon or fish, I think oftentimes children don't like looking at, they will then reject it. In fact, chicken, a very common one with, I think, American children, would be they like the smell of fried chicken, but if they see these strange black dots, which are just either burned pieces from the frying or possibly a piece of pepper, the black dots oftentimes turn them off and they just won't even touch the food. In fact, you even see that as well also with children with food touching each other. And that's why for children's plates, they oftentimes have 3 sections in them. That way there's 3 wells and you could put peas in one, potatoes in the other, and meat in the third. And that way it keeps the food from touching each other. Because for reasons I'm not going to get into, children seem to be bothered by their food touching each other, and therefore they'll reject an entire plate of food even when they're hungry because some of the peas rolled over and touched a piece of chicken. How about this question? Which principle is reflected in the following scenario? You hate to gossip, but with some people you actually enjoy it. Okay, if you hate to gossip, but with some people you actually enjoy it, then that means it's context specific. And if something is context specific, it is a Gestalt. Gestalt always refers to the context in which something occurs, influences how you perceive it. It's never the thing itself, it's always the entire context in which it occurs, and that is the primary aspect. Now this last question. Which principles reflected in the following scenario? You drive out of your lane while texting. Well, this one is probably obvious just because of the times that we live in, and that's going to be attention. The aspect of attention, if you're not paying attention to driving because you're using your cell phone, then you may get into an accident. Now, why do some of these perceptual aspects occur? Well, they actually occur from a mixture of issues that we've talked about over the past few chapters. Starting with brain plasticity or neuroplasticity that we talked about back in the neuroscience chapter, your visual system is wiring itself as you're an infant before the time in which you have language. And so as you're looking around the room, but you can't crawl, and then months later you can crawl and you're still looking around the same room, you begin to detect the objects in the room and how they change in size and shape based upon how close you can get to them. So obviously, anything you get closer to always appears larger in your visual system because you're closer to it. And anything that you get very far away from always appears smaller. Now, as a child, it's possible that you learn to some degree that things are actually changing size. But as you start becoming more mobile, you realize that things stay the same size, but they look larger or smaller based upon your distance to them. Which means your visual system gets wired in to detect the size of an object to reflect its distance from you. And as you lose your neuroplasticity at sometime around age 12 or 13 to the standard adult level, which is not a whole lot, you are now stuck with the circuitry that has been wired into your occipital lobe. And even if you have complete rational knowledge of the size of an object, you will still always experience certain types of visual illusions simply because of the way your nervous system is wired together in your occipital lobe, which you can no longer manipulate because it's now settled by the biological parameters that have made you an adult. One other instance of this, apart from the sizes of objects and how close and far they are from you, is this visual illusion you see on the screen on the right-hand side. This is called the Mueller-Lyer illusion, which again, you know must be a very old one because the two people that invented it were Mueller and Lyer. Now, take a look at line segments AB and BC. Now, not trying to get this right, perceptually, which line segment seems shorter? Does line segment AB appear shorter, the same as, or longer than line segment BC? Well, line segment AB for most people will appear to be shorter than line segment BC. But as you might imagine, line segment AB and BC are actually the same length. And oftentimes in these types of scenarios, you can even make line segment AB longer than BC, but AB will still appear to be shorter. So why does this occur? Well, as you might imagine, it probably has something to do with these side line segments that look like arrows. And that actually is very much the reason why this is happening. Take a look at points B and C. Those are like the lines you see in the corner of a room. Line segment BC would be the vertical line between two walls, and then the ceiling would be the shape of that upper portion of the arrow, and the floor would be shaped like the arrow at C. That indicates that a thing is moving away from you, right? This is a corner that's away from you. The opposite is seen in AB. Because you live in a world that's made by carpenters, you essentially live in boxes. Houses and schools and all buildings are essentially somewhat box-shaped. Line segment AB reflects a portion of a wall that would jut out toward you. So like the corner of a building. If you were looking at the corner of a building, the sidewalk would look like the arrow at point B, right? Going back in two directions. And the roof of the building would curve down as at point A. If two lines are the same length, AB and BC, but one has a Q that it actually juts out towards you, and the other one has a Q that it juts out away from you, then line segment BC must actually be longer than line segment AB because it's actually farther away. BC has to be farther away. And if it casts the same size image on your retina, it actually has to be longer. So you have this impression that segment BC is longer than segment AB. This issue, even though you could sit here with a ruler and measure it and know rationally that it is not that the segments are the same length, you still can't stop yourself from seeing it simply because your occipital lobe is correctly wired in the circuitry for you to determine distance. And in this particular case, when you pull out aspects of that visual experience, you can then cause an illusion. So, how about some general questions about perception? Do all perceptual illusions occur through the same process? No, they do not. There are illusions in which similar sensations appear to be different, like the Mueller-Lyer illusion we were just looking at. Line segments A, B, and BC were the same length, but they appeared to be different. Or Shepherd's tables. Here in Shepherd's tables, these two tables have the same size, but they very much don't appear to be. So if you stop the video and measure the top surface of these tables, you'll see that they're the same. But this visual illusion is especially strong. And it's because of the angle, vertical or horizontal, of these two tables. There are also visual illusions in which different sensations appear to be the same, like color constancy, where you can have different wavelengths coming into your eye, but be made to believe that the color is the same, and shape constancy as well, which we haven't talked about until now, in which if you're looking at a person, for example, and that person rotates 360 degrees, like they're pirouetting, You clearly are detecting a changing shape on your retina as that person spins in front of you, but you don't have an internal perception that they are changing their shape, but rather that they're just rotating. And so the concept of shape constancy is that you believe that the shape is the same despite the fact that you are detecting different sensory experiences. So what can you believe after this introduction to sensation and perception? Essentially, the answer is nothing. Okay, and I know that seems rather extreme, but in all cases, it should be clear to you, going back to Weber's law and the just noticeable difference of Fechner and the aspects of psychophysics that we talked about and all the perceptual illusions that we dealt with in terms of vision, you can't truly expect to experience accuracy for any sensation at all. You simply have to have various measures and experience with things to make sure that you understand them correctly. So the only way to tend toward accuracy is to take measurements of the world. Make sure that they're objective measurements and that they're read properly. Not only that, but these concepts of sensation and perception are not just concepts that apply for determining the difference between various shades of blue or the size of an object that's across the room. If that's all we were talking about, then most of this would really not be that important. What we are looking at is that these are all basic rules for understanding how humans perceive the world. And as a result, you can take these basic rules of sensation and perception and apply them to social scenarios across your life experience, and you will wind up finding that these same rules apply for detecting whether or not your friend is slowly becoming depressed, whether or not your boyfriend or girlfriend is starting to act odd. How likely is it that you think something's going to happen with respect to the country based on the stories you see on the television? These are all aspects in which you're going to have to notice a difference. And that noticing of a difference will be determined by the just noticeable difference process for a very wide range of types of stimuli that you're experiencing. So these characteristics establish a very basic process by which all experience can be filtered through, and you have a strong mathematical basis to understand the distinctions that you make in the world and where those ideas come from. So it really becomes a substantial part of the basics of underlying psychology, because there's no aspect of your experience any day or throughout your entire life in which sensory and perceptual phenomena are not occurring. And so these processes always operate, and they affect everything that you do. So to guard against your misperceptions, which are very likely to occur, there are just some basic rules to follow that everybody should follow. Question your own assumptions. Accept that you may sometimes be wrong. Keep an open mind, persevere, and probably the best advice that I can give you, use the scientific process. Try your best to apply logic, keeping an open mind to try to understand people, the world, how anything operates. Don't become overly connected to any one explanation, because something that seems very obvious may wind up being completely wrong in the end. And that concludes our discussion of sensation and perception.